for the delta Springer module.
Thank you, and thanks for having me here virtually. It's very good to be here. Thanks to the organizers for setting this all up. I'm going to talk about a cocharge formula for the delta Springer modules that me and Sean Griffin worked out, and it's a conjectural formula, but we have a lot of special cases, as we'll see. So here is a battery-powered tableau, or at least a funny picture of one. There's actually going to be a thing called a battery-powered tableau that we're going to compute the cocharge of to get the graded Frobenius of the delta Springer modules. So to introduce the delta Springer modules, first I want to warm up with the co-invariant ring, which we've seen a couple times in this session. So R sub n is Q adjoin x1 through xn mod the elementary symmetric functions. You're modding out by the invariance under the Sn action on the n variables. And so this has connections to geometry. It's the cohomology ring of the complete flag variety. It has an algebraic structure of an Sn module by permuting the variables because the ideal is invariant, and it's a graded Sn module as well. And it also has some nice combinatorics. So we know it's the regular representation of Sn. It has dimension n factorial, and the graded decomposition as a graded module, but graded by the degree of the monomials, is understood via the cocharge statistic on Tableau. So this was by Lescaut and Schuster-Roget. They introduced cocharge. And we'll be using the French notation for standard Young tableau and semi-standard Young tableau here. So standard is increasing in rows and columns. Semi-standard can have repeats in rows. And the content is the tuple indicating how many ones, how many twos, how many threes, how many fours there are in a semi-standard Young tableau. And the shape is just the shape of the tableau. So we will use shape and content a lot in this talk. And the Schur functions we all know, so I'm going to just skip over this definition. They've been mentioned quite enough times in this session already. The Frobenius map is the one that sends an irreducible representation V lambda of the symmetric group to the Schur function S lambda. And then it's additive across direct sum. And so the Frobenius series, the Frobenius character of any representation of the symmetric group is a Schur positive symmetric function, a sum of Schur functions. And so what we need in this talk is the graded Frobenius, which is really just the generating function of the Frobeniuses of each graded piece when you have a graded representation of Sn. If it's graded by degree d, you take q to the d times the Frob of Rd. So as an example, going back to the co-invariant ring, the graded Frobenius of Rn is the sum over Q to the cocharge of the tableau, where you sum over all standard Young tableau of size n, so any shape, and you take the Schur function of the shape of the tableau, and then this cocharge statistic is something we will be defining and generalizing later. Okay. Is there a chat that I missed? Or oh no, sorry, I thought there was a question. Okay, so then let's generalize this Rn story to, first of all, the Garcia-Procesi modules, which we've also seen in this session one time. So Raymond talked about a basis for these. These are R mu, and they're quotient by more than just the elementaries. You also have these partial elementary symmetric functions in subsets of the variables S with some bound on the degree. And there's connections again to geometry and combinatorics. So they're the cohomology rings of the Springer fibers, and the combinatorics is also governed by a cocharge statistic. Here we're summing over the semi-standard Young tableau of content mu. So mu, the partition, is determining the content of your tableau. They can still be any shape with that content. And then you have a cocharge statistic telling you the power of Q attached to S of the shape of that tableau. And that's the graded Frobenius character of this R mu. There's another generalization in a sort of different direction by Hagelin, Rhodes, and Shimizono. The modules R and K, where you mod out by some of the elementary symmetric functions, the ones bigger than n minus k, and also the kth powers of every variable. This is also, still invariant under the action of Sn. It still has a graded Sn module structure, and it has a lot of different connections to geometry. We'll see another one soon, but the first one was found by Pulaski and Rhodes via line configuration spaces. And in terms of the combinatorics, there's a lot of interesting combinatorics in these modules. They came up actually as the graded Frobenius came up at the t equals 0 specialization of the polynomials that arise in the delta conjecture. And there's formulas for them involving ordered set partitions that express it in terms of monomial symmetric functions or in terms of Hall-Littlewood polynomials. There's a lot of different expansions of this graded Frobenius. But what is missing so far is a cocharge-like Schur expansion like this one, where you just have a single sort of object you're summing over and some cocharge statistic and telling you what the coefficient of a Schur function is. So we're going to sort of answer this one today as well, because it's a special case of the more general result that we have. And the more general results is on what we call the delta Springer modules, delta because of the delta conjecture connections here, and Springer because of the Springer fibers. You put them together and you get a common generalization that Sean Griffin came up with in his thesis called Rn lambda S. So I'm just going to take a moment to tease Sean about his notation, as I always do, which is lambda here really is sort of like the mu in the Garcia-Protesi setting, and S is very much like the K in the Hagelin-Rhodes-Shimazona setting. In fact, if you look at these specializations down here, if you plug in lambda equals mu and S equals n, then you get the R mu, and if you plug in S equals K and then lambda is 1 to the K, you get RnK. So that's how it generalizes the previous two settings, and it's even defined with Tanasaki-like generators in almost the same way, but also modding up by the X side of the S's. So it really is a common generalization, and then it has nice geometric understanding in terms of these new delta Springer modules that Griffin, Levinson, and Wu recently came up with, which also gives a different understanding for the geometry here. And then the combinatorics also has there's also lots of formulas for this. So Griffin has some formulas in terms of in statistics, giving the monomial expansion and sums of Hall-Littlewoods. But again, we want a cocharge-like Schur expansion that just sort of directly tells you what the graded decomposition into SN modules is. And so that's what we're going to talk about today. So to state our conjectured formula for the graded Frobenius, we need to define a few objects. The first object is what we call the total partition content. So first of all, let me say that this Rn lambda S is defined when the size of lambda is at most n, and S is any number that's at least the length of lambda. So keep that in mind when we have any n lambda and S. And then for such an n lambda and S, we define the total content partition to be this capital lambda sub n lambda S, to be the partition formed by just adding a bunch of n minus k's to the beginning of each part of lambda, where we pad lambda with zeros to make it length S. So as an example, if S is 4 and lambda is 2, 1, 1, first of all, you pad lambda with zeros to make it height 4. And then you add a 4 by n minus k box here. Here I have the example n equals 9, and k here is the size of lambda, which is 4. So 9 minus 4 is 5, so n minus k is 5, and you add a 5 by 4 box, a rectangle, to the front of lambda, and that forms this bigger partition, capital lambda, which we're going to use as the content of the object that we're defining. Okay, so the first thing we need to understand is this new content that you just put n lambda and S together and you make this picture. Then once we have this content, we define a battery-powered tableau. So here's the new object. You have a battery-powered tableau is a pair, D comma B, where both of these, D and B, are both semi-standard Young tableaus. So you see I have a D up here and a B down here. D we call the device, and B we call the battery. Notice the battery is rectangular. It is always rectangular. So B is a shape n minus k to the s minus 1 rectangle. So it's just one height less than that rectangle we added to form the partition content in the previous slide. And then D is anything, and the only thing we require is that this whole thing, D plus B together, the content of that total tableau is this capital lambda that we formed. So this is the same numbers as in the previous example. Capital lambda is 7665, and that means there's 7 ones total in D and B, and 6 2s total, and 6 3s total, and 5 4s total. So that's how we define a battery-powered tableau for parameters n lambda and S. And we define the shape of a battery-powered tableau to just be the shape of the device. We don't worry about the battery. We don't take the shape of the whole skew tableau, right? We do draw them diagonally down and right for a reason that we'll see soon, but It's just the shape of the device. So here the shape is 621, and the we write T plus, like this fancy T plus, to be the set of all battery powered tableau for n, lambda, and s. The little plus is like we're adding charge with a battery. So we're like charging it up. Okay. So speaking of charge, let's talk about cocharge and charge. So here's how we define cocharge on actually any tableau or any word. We're going to just take the reading word of this tableau in order, right? 4, 3, 3, 1, 1, 1, 2, 2, 2, etc. Read from top to bottom. And we're going to use that reading word to compute the cocharge of the entire thing, D union B. To do that, we search in reverse reading order cyclically for a 1. So you start back here, down at the bottom, and you go left until you hit a 1. And you label that with the first cocharge subscript. The cocharge subscripts start at 0, and they increment each time we get to a new number unless we wrap around the whole tableau, then they don't increment. So we continue doing this. If we continue from our 1 search to find a 2, we find that one, we label it with a 1. We continue our search to find a 3, we label that with a 2. We continue our search until we find a 4, and we label that with a 3. When we get to the highest number, we just start over. We eliminated all those, that 1, 2, 3, and 4, and we start at the bottom and look for the first unmarked 1. There's a 1. We label it with a 0. And then you go up to the 2 and the 3. Now, in this case, we do wrap around. This 4 is already used, so when we get to this 3, we wrap around the tableau to find this 4. And since the last cocharge subscript was 2, we do not increment it, and the next label is 2. You keep doing this. You start over to find a 1 again, label it with a 0, keep going. I'm just going to sort of advance through. You see how we keep labeling until the entire thing is labeled. And finally, when it's all labeled, the cocharge is defined as just the sum of the subscripts that we've put there. And for the charge, which is the sort of dual of cocharge, you increment when you wrap around, and you don't increment if you don't wrap around. So they're just dual constructions. So here, the cocharge of our T plus here is 23. If you add up all those subscripts, it's a quite large one. And one very important property of charge and cocharge that is already known is that it is invariant under, Knuth equivalence, RSK, JDT, the whole Plactic monoid, which means it has this fun property that if we literally insert the battery into the device, meaning RSK insert it, then it doesn't change the charge or the cocharge of the entire thing. So we really are inserting a battery into a device and calculating how much charge it has. So now we can finally state our conjecture in terms of these battery powered tableau. So I'm going to write H tilde n lambda s xq as a shorthand to denote the graded Frobenius of Rn lambda s, because in the case where it's just R mu with the Garcia-Procesi case, this is the notation for the Hall-Littlewood polynomials. So I'm stealing that notation and just generalizing so I don't have to write graded Frobenius sub q every time. So let's just calculate these h's is just the graded Frobenius we want. And so what is that? Well, it's 1 over q to the, so there's a q power out front. Actually, I'll define that in a bit. What I'm doing is I'm summing over all battery powered tableau T plus of q to the cocharge of T plus times s of shape of T plus. Remember, the shape is the shape of the device, and the cocharge is the total cocharge we just computed. And what this number is that we divide out by is actually just the maximum, this s minus 1 choose 2 times n minus k is the maximum amount of cocharge that can be stored in the battery. So if you look back at this diagram, you'll notice this has 0 subscripts on the first row, and then some 1 subscripts on the second row, but there's a 0 in here too, right? And then some 2s on the third row. The maximum cocharge you can have is all 0s on the bottom, and then all 1s in the second row, and all 2s in the third row, and so on in the battery. And if you add that all up, that total amount, we just divide out by that. So what we could do, if we wanted to simplify this further, is define a modified cocharge statistic, where we just define the cocharge of a battery powered tableau to be the way we calculated cocharge minus this constant, right? Subtract out this total from the battery. And what that would do is have a single cocharge statistic and a single object that we're summing over it that gives an exact analog of the Lescush-Berger formula. So that's our conjecture, and we can prove that it's equivalent to the following charge version of the conjecture, where you just do a Q reversal, meaning you reverse all the powers of Q. You take the maximum power of Q, in this example, Q to the third, and you replace the Q to the thirds with ones and the Q squareds with Qs and so on, and you get the Q reversal. And with the Q reversal, what's nice is cocharge turns into charge, and you do get rid of this funny multiplier. So it's a little bit cleaner of a formula to write. So as for partial results, how far did we get proving this conjecture? Well, coming up with it was the hard part for sure. But in terms of how true it is, well, the computer sage told us that it is true for all n less than or equal to 8, with all lambda and all ns at most length of lambda plus 7, which is quite significant because remember we're searching over not for each n at up to 8 every possible lambda partition that is size at most 8. So you have the partitions of size 8 and the partitions of size 7 and so on. And then for each of those, all the s's, that could be even 7 higher than the length of lambda. So it's pretty thoroughly tested. We also did 9 and 10 for smaller s, and we're pretty sure this is true. We have some sort of heuristic reasons why it should be true, as well as proofs for some special cases. So this is one of the special cases is when n minus k, the size of lambda, is 1. We have a sort of geometric proof of this using the connection to the Spaltenstein variety, the connection of the delta Springer varieties to the Spaltenstein variety. So that one just sort of came out of the theory. And then s equals 2, we were able to prove using the known Hall-Littlewood expansion of the graded Frobenius and just comparing it directly to our formula using the Lewis-Kuschitz and Berger formula. But that method didn't extend past s equals 2 as far as we could figure out. And then we also found some coefficients for the RNK case. So in the RNK case, we looked at the sort of mini-Madge formulas, and there's this crystal theoretic understanding of its expansion using ordered set partitions, and Schilling and other people were studying this. So we use those kind of formulas and some other things to get a sort of combinatorial proof of at least the Sn coefficient, in this case, the coefficient of the Schur function Sn. And then recently we got the Q equals 1 specialization, which means at least numerically, like the non-graded Frobenius is correct. We have a proof of that. So it is given by the battery powered tableau if you just forget the cocharge statistic altogether. And the interesting thing is the way we were able to prove this Q equals 1 setting was actually via another new result that I'm going to state on the last slide, which is using the Hagelin-Morse-Zabraki creation operators that came up in the compositional shuffle conjecture, and the abacus formula by Lauren Warrington for that. Now I have a little surprise for Sean here, which is this morning and yesterday I was working we keep working on these special cases, and it's a matter of like, when do we stop, right? And Sean, I think I have the Sn coefficient for s equals 3, and lambda 1 is at least n minus 1 over 2. And I'm putting question marks because it's like on my notebook, so I need to show Sean on Tuesday and we'll verify whether or not this is correct. But I added this to my slides this morning. So anyway, the last two, both this Q equals 1 and this new thing that I think I have that I think we'll be able to generalize, we're using these creation operators. So the last thing I want to talk about is that there's these creation operators CM by Hagelin-Morse-Zabraki that are defined with this funny formula in terms of, plothistic substitutions and perps, and it's an operator, right? And you can compose them to construct Hall-Littlewood polynomials. So this is a known formula. By composing some of these with some Q power, you get the ordinary Hall-Littlewood's. And Lauren Warrington have a combinatorial abacus model, like I said, to compute what a creation operator does to a Schur function if you want its Schur expansion. And we were able to show that we have not only do the Hall-Littlewood's not only can the Hall-Littlewood's be constructed in terms of these, but so can the delta Springer Frobeniuses. So our H tilde n lambda s has a recursive formula in terms of using a creation operator on previous ones where you sum some of them together. And so it's a recursive formula that we have. And then using that Lauren Warrington abacus formula, the hope is we could prove it by induction, the conjecture by induction, where you put the battery powered formula in here, you apply the abacus formula to each of those Schur functions, and then you see what the resulting sort of cocharge looks like and hope that it matches what you want on the left-hand side. So you can also unwind this recursion to get, a sum of these compositional Hall-Littlewoods. So these are the compositional Hall-Littlewoods, where it's not necessarily a partition on your subscripts. And we have a formula, a decomposition now in terms of the compositional Hall-Littlewoods. And just for fun, we can actually just sort of plug in the compositional shuffle conjecture, which was proven by Carlson and Mellett, to get a formula for the Nabla operator applied to H tilde and lambda s in terms of parking functions and area and div, just because that's what these, this summation tells you. The compositional shuffle conjecture tells you that this composition of creation operators has a formula like this. So that's our last result, and thank you very much for listening.
Anyone have questions for Maria?
Just had one question. So is it known whether or not these H tilde lambda ns are sums of LT polynomials?
Oh, are they sums of LT polynomials?
Yes.
Sean says yes.
But
Wait, do we know? Yeah, there is a formula for that. I forget what the formula is. Is there?
Okay.
Formula, right?
yeah, so there are 3 formulas. One is a modified Hall-Littlewood expansion, and then 2 others that are different LLT expansions, where the LLTs that appear aren't necessarily Hall-Littlewood. One is like a dim, and the other is like an in.
Because there's a formula by these Heyman, this group, for Nabla of any LT.
I see. So maybe we could look at so you're saying maybe this isn't like new from this formula because we could have just expanded in terms of LLT and apply the Heyman formula for Nabla of the LLTs?
Right, and that might even uniquely define function that might prove it.
Yeah, maybe. Yeah, I don't have the formula the formulas in terms of LLTs like in my head right now, so I'm not sure how that would look. But yeah, that's a good thing. That's a good idea. It's a good thing to look into.
Anyone else have a question? And let's thank Maria again.
Thanks.